Bridges are one of man's most complex and widely utilized creations in transportation. Whether they span the width of a small stream or a major body of water, bridges must be stabilized to withstand an incredible amount of force. How is it that automobiles, each with substantial mass, are able to travel over bridges without them collapsing? It seems that a bridge would collapse simply from the gravitational force exerted downward from the building materials. At the same time, when an object of any mass is located on the bridge, it contributes to the forces exerted on the bridge's structure. The magnitude of this force can be calculated using the equation force equals mass times acceleration, where A equals the acceleration due to gravity, or 9.8 meters per second squared. But if all of these forces are exerted downward on a bridge's surface, how does it stay erect? Much like any classic physics problem, there exists a normal force equivalent to the weight of the bridge, exerted in the upward direction, that acts on cars, pedestrians, and materials to keep them lofted. In order to construct these fascinating structures, great analysis must be done, and a great deal of time is required. Now let's look at different types of bridge structures in turn and examine how the forces are distributed in each. Some bridges, like the Rialto Bridge in Venice, Italy, utilize arches to reinforce structure. Arches are made by stacking trapezoidal stones or blocks on each other, with the truncated wedge facing the arch's interior. Each individual piece of an arch is called a voussoir. By placing voussoirs in contact with each other, they exert forces on neighboring voussoirs that allow the arch to remain intact. An interesting aspect about arches is that no cement is required to build them. In this demonstration, you can see that we can build an arch structure that is held together simply by the forces that act on each voussoir. Forces of friction stabilize the voussoirs and help to prevent them from sliding outward from one another. The force of friction is denoted Ff in this demonstration. The normal force exists tangentially to the contact surface and is denoted Nf. The horizontal and vertical forces in the figure relate these two voussoirs with respect to the level ground on which the arch is placed. In order to find the magnitude of these forces, we can use the equations horizontal force equals the friction force times cosine theta plus the normal force times sine theta, or the vertical force equals the friction force times sine theta plus the normal force times cosine theta. We can break apart the figure into triangles and see how each variable in the equation relates to how the forces are exerted between voussoirs. If this arch, which has substantial mass, can remain erect without any cementing, imagine how strong an arch is with strong, resilient cement. This makes arches suitable structures to use in bridge design because of how durable they are, and the manner in which the forces are distributed throughout the structure. The arch in the demonstration was at equilibrium because no part of it was moving, but when external forces are added to an arch, its equilibrium position shifts. As long as no voussoirs can move outward, then there is no room for other parts of an arch to fall, and it will remain intact.
In the world of architecture, a truss is a physical structure built up of one or more triangular units whose ends are all connected at joints called nodes. External forces and reaction forces only act on these nodes and result in forces along the segments of the triangles in either tensile or compressive forces. Depending on where the weight is in relation to the structure, the segments will either be under tension or compression. Tension can be described as the pulling force exerted by one object on another, which results in the forces pointing towards the joints. Compression is the application of balanced inward forces to different points of a structure. Because this is an inward force, the force will be pointing towards the middle of the segment, away from the joints themselves. Since a sturdy object like a bridge isn't moving, we can say that the sum of the forces is equal to 0 because the structure is not under any acceleration. Similarly, because of that equation, we can also say that the sum of the torques is equal to 0. We can use this information to help find the forces that a truss structure is put under. If we consider a bridge with 2 supports and a weight of W, we know that, because the sum of the forces is equal to 0, that R1 plus R2 minus P is equal to 0. In situations like these, we can find both R1 and R2 by simply being given the weight and structure undergoes. By finding the force that a certain segment is experiencing, we can use that as a piece of the puzzle in helping us to find the other forces the structure is experiencing. Because the forces act on the nodes, we can separate a truss system by the amount of joints there are. By finding the force that each joint undergoes, you will have found all the forces that the truss as a whole undergoes. Suspension bridges work in very similar ways as trusses, in the way that the nodes or joints are being acted upon by the forces of the system. There are many variables that go into finding these forces. Force that a suspension bridge undergoes depends on things such as the distance, d, between the vertical supports, n, the number of vertical supports that are present, l, the distance between the leftmost and rightmost vertical supports, and also w, the weight that each vertical support holds. Because a suspension bridge has many diagonal segments, each node has to be separated into x and y components. As we discussed with the truss, the sum of the forces is equal to 0, and the sum of the torques is equal to 0, because the suspension bridge isn't undergoing any acceleration.